Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is our next problem. Problem having been chosen from the book Modern Physics by Kenneth S. Crane. Okay. As usual, we first come to its statement. Okay. Statement of the problem is use the Wiedemann-Franz ratio to calculate the thermal conductivity of copper at room temperature. The electrical conductivity is 5.96 into 10 to power 7 per ohm per meter. Okay. Quite similar to previous problem. Here once again it is important to point out here that this value, that is rho, electrical conductivity, 5.96 into 10 to power 7 per ohm per meter, is also given in a lot of tables used in the books of solid state physics. Okay, and hence even if this value is not given here, we can take it from those tables. The second point is that for the purpose of this problem, or for in general, we are assuming 20 degrees centigrade as room temperature. Okay, because dear students, weather varies, summer to winter, temperature varies so many times during year, so it is enough difficult to fix some temperature as room temperature. So, according to some international standards, presently room temperature is assumed to be 20 degrees centigrade. This temperature can be converted into Fahrenheit and then Kelvin. When we convert it in absolute temperature Kelvin, then this figure becomes about 293.15 Kelvin. Okay. So instead of 293.15, in most books 300 Kelvin is taken as a room temperature. Okay, so 20 degrees centigrade or 293.15 Kelvin or 300 Kelvin is usually regarded as a room temperature. Okay, now we move to helping tools. Okay, first helping tool. In first helping tool, copper becomes at serial number 2. In this table, resistivity as well as conductivity both are given. Okay, copper resistivity is 1.72 into 10 to power minus 8 ohm meter, while its conductivity is 5.81 into 10 raised to the power 7 per ohm per meter. Actually, dear students, from here we can conclude, or we can estimate, but rather if we do not estimate, it is a clear cut fact that resistivity and conductivity are reciprocal of each other. Okay, less resistivity, more conductivity, and vice versa. Okay, so dear students, we can see that when we inverse 1.72 into 10 to power minus 8, we will get 5.81 into 10 to power plus 7. Okay, it is quite clear that in case of resistivity, its units are ohm meter, while in case of conductivity, its units are per ohm per meter. Moreover, in case of copper, resistivity is 10 to power minus 8 while conductivity is 10 to power plus 7. Okay, so it is quite clear that when we take inverse or reciprocal of 1.72 into 10 to power minus 8, we get 5.81 into 10 to power 7, and when we take inverse 1 over or reciprocal inverse of 5.81 into 10 raised to the power 7, we get 1.72 into 10 raised to the power minus 8. Okay. Now, in table number 2, electrical conductivity of copper has been given as 59 into 10 to power 6 per ohm per meter. Okay, this value is also given in the statement, but if not given in the statement, we can take this value from tables. Okay, at helping tool number 3, Lorentz number has been described. This is Lorentz number. Okay, in relativity, general relativity or classical relativity, in general relativity or special relativity, we deal with the term Lorentz. Okay, Lorentz was a scientist, and Lorentz may also be a scientist. So it is clear that here in solid state physics, this word is L-O-R-E-N-Z, Lorentz. While in while in special relativity or general relativity, the word or term used is Lorentz. Okay, in between N and Z, T comes. Okay, now Lorentz number is equal to pi square k square over 3e square. These values, all these are constants. Okay, value of pi is 3.14, value of Boltzmann constant k is also given in table of physical constants. Similarly, elementary charge E is also given in table of physical constants. Okay, hence when we simplify all this expression, we get Lorentz as equal to 2.44 into 10 to power minus 8 watt omega over Kelvin square, k square. Okay, dear students, actually the alphabet K is used to denote several things. Okay, it is also used to denote Kelvin temperature. It is also used to denote Boltzmann constant. It is also used to denote thermal conductivity. It is also used to denote kinetic. Okay, so in next to this, its alternate version has also been given. Okay, so these two snapshots both these snapshots have been chosen from the book Modern Physics by Kenneth S. Crane. The only difference is that second version has been chosen from the in between the chapter. Okay, so 11.221 is the equation number of 11th chapter of Modern Physics by Kenneth S. Crane, while first version, that is which appears as if it is equation number 11.3, actually it is not equation number 11.3. It indicates that this expression belongs to third topic of 11th chapter of Modern Physics by Kenneth S. Crane. Okay, so in its alternate versions, Lorentz number L is same. Okay, no difference. Now we move to helping tool number 4. Okay, the helping tool number 4 is that table which has been used so many times in our problems, in our videos. So for the time being we omit, we skip, we ignore explanation of this tool. Okay, now we come towards the solution. Okay, we know that according to Wiedemann-Franz law, L is defined as, dear students, these three lines are understood as is defined as. Okay, is defined as are equal to, are almost same, but some difference also exists. Okay, if we say that L is equal to K over rho T, and if we say that L is defined as K over L, rho T, then definitely some difference also exists. Okay, so two lines denote equality while three lines almost denote equivalent significance, or is defined as. Okay, so L is defined as K over rho T. This implies that K becomes equal to L into rho into capital T. This is equation number 1, where capital L is the Lorentz number, okay, which we have mentioned above in helping tools. Okay, rho is the electrical conductivity. Okay, in various tables we have discussed that electrical conductivity is denoted by rho, while thermal conductivity is denoted by capital K. Okay, and capital K is thermal conductivity and T is the absolute temperature. Okay, here we are dealing with the absolute temperature at room temperature, which is about 20 degrees centigrade or 293.15 Kelvin. Okay, we know that usually room temperature is taken as 20 degrees centigrade, alternatively equal to 68 degree Fahrenheit, alternatively equal to 293.15 Kelvin. Okay, hence putting these values in the equation, okay, K becomes equal to 2.44 into 10 to power minus 8 watt omega over Kelvin square into 5.96 into 10 raised to the power 7 over into 1 over rho meter into 293 Kelvin. Okay, dear students, here we have used 293. Okay, we have ignored 0.15. Okay, so K becomes equal to 4260.92 into 10 raised to the power minus 1 watt over Kelvin meter. This becomes equal to 426.092 watt over Kelvin meter. Okay, because this 10 raised to the power minus 1 will reshape this quantity as 426.092. Okay, previously it was 4260.92 and now it has become 426.092 because it has been multiplied with 10 inverse. Okay, and hence our value of K has become equal to 426.092 watt over Kelvin meter. And this is the end of our problem. This is the end of our video. Till next video, Allah Hafiz.